Greetings to everyone on this call today. I welcome you all to today's webinar on multi-user run-off electronic sensor platform. Just a few housekeeping notes. Today's session is being recorded and all the participants are muted by default on entering the webinar. I'm Priya Mangannavar from CMC Microsystems. In today's webinar, after an introduction to CMC, I'll be talking about the electronic sensor platform and the reference designs that CMC has developed. At the end, I'll also talk about how you could participate in the upcoming run for this technology. This technology was developed in collaboration with 3IT, University of Sherbrooke, where the fabrication takes place. I have with me Marie-José from 3IT, who would be talking about the fabrication process and some of the design considerations. Today, we also have two user presentations who were part of our previous run. Mehrani and Abbas, both from York University, would be talking about how they use this platform for their research in their particular application. I would request you all to please ask your questions through the chat window as we would be pausing after each presentation to take the questions. I would also request you to please send the chat question to everyone instead of the specific speaker. To begin with, let's get started with knowing a bit about CMC. CMC Microsystems is a not-for-profit organization with a mission to lower barriers for technology adoption. We are the managers for Canada's National Design Network, CNDN. In our mission, CMC delivers micro-nano innovation capabilities across Canada, and broadly speaking, deal with technologies that will enable Canada's digital economy of the future. The National Design Network is a Canada-wide collaboration between 67 universities and colleges, and it connects about 10,000 academic participants with 1,000 companies to design, fabricate, and test microsystem prototypes. This shows the breadth of participation across Canada and the outcomes that we have achieved. We also give our clients a competitive advantage by bringing our global chain of supply partners to their very desktop. The infrastructure and services we provide is divided into three main categories: CAD, which delivers design tools, platforms, and compute infrastructure to design and develop micro and nanosystem prototypes. We deliver these capabilities either through the cloud infrastructure or on the user's desktop. We also provide fab services, which is multi-project wafer services, package and assembly, fabrication and travel assistance to manufacture prototypes in commercial or university-based labs. Under lab services, we provide short-term access to development platforms, test equipments to validate and emulate test prototypes. We also provide services for emerging processes and products. The process we are talking about today, the electronic sensor platform, is one such example. It was first demonstrated at a university lab and now has grown to become available to users across Canada and beyond. At its core, the electronic sensor platform, or ESP, consists of a silicon junction field effect transistor. In this technology, the transistors are delivered without an upper gate, which allows the integration of a functional material directly onto the semiconductor channel. The functional material acts as the upper gate to modulate the channel conductivity. This image shows the silicon JFET with the different layers. Now, this flexibility in depositing the functional material of your choice makes this platform suitable for a plethora of applications. The first application for which this platform was developed was for optical or photo detection using colloidal quantum dots as the functional material. This application was successfully demonstrated and has in fact generated a Nature publication. Since then, this platform has diversified into several other applications, especially in the field of biosensing. Further in this webinar, Mehrani will be talking about how she has used graphene as the functional material and used it for pH sensing. And Abbas will highlight how they are detecting neutrophils from saliva for early asymptomatic detection of COVID-19. Now, for you to start working on all these exciting applications, CMC has developed a process design kit. The kit consists of a user guide, LEDit layout template, along with the DRC deck, reference design, and simulation files. We have Synopsys Centaurus models of the colloidal quantum dots application. Also coming up very soon are ComSolve multiphysics models. In the LEDit layout file that you can see here, we have what are known as the cells, and we have also recently developed what we call as the parameterized cells, in which you just need to plug in the channel length and width, and a JFET cell is automatically generated. The flowchart on the right shows the activities a designer would typically follow to prepare a layout and simulation using the PDK. Once you have completed the design, it can then be submitted to 3IT for fabrication. After fabrication, the chips are delivered to the designer for integration of a soft material and further experimentation. Now, to help you with your design, CMC has developed two reference designs. The first one is a 5mm by 5mm design, the layout of which is available to you in the PDK. This particular reference design comes with multiple channel lengths, which could be useful for you to test and narrow the dimensions of your final design. We can also make this die available to you if you want to test your idea before going into designing your own. We have tested these chips at 3IT, and they show the expected transistor behavior. These are bare dies without any open gate at the top, so allowing you to deposit the top material that you want to deposit. The other design that we have is that of a fluidic sensor. The layout has been designed such that a fluidic channel can be interfaced along with it. And this is especially useful for biosensing applications. This is a 10mm by 10mm chip design, and we have two variations of this. One which has a wide channel as shown, and one which only has a straight channel. To go along with these chips, we also have developed a microfluidic package through 3D printing. We want to ensure that you're able to start using these chips directly without having to spend a year of research time tinkering with the fluids. There's a lot of work being done in this field. Oleg, who is on this call with me today, is closely associated with it. And please feel free to reach out to us for more information if you're interested to know more about this. This concludes my first section. Now, the next segment of presentation is from Marie-José, who would be talking on the fabrication aspects of JFET. Marie, over to you.
All right, so welcome everyone. I am Marie-José Gault. I am a research professional at 3IT at the University of Sherbrooke. So we are the ones that are making these devices. So for those of you who are unfamiliar with what 3IT is, in 2012, the University of Sherbrooke made a new building where 49 researchers from the engineering faculty and physics department moved into. The difference between our building and the typical lab usage that is done on the university campus is that the members here put their equipment as a general access to all users. So researchers don't have their own labs anymore. We have infrastructures that are placed in common for all users. So anyone that is properly trained on an equipment can use the equipment. So today we have over 60 members, actually close to 70, across a very broad range of faculties here and universities. The goal is really to act as an incubator to scientific and technological innovation. So as I was saying, we have different infrastructures. So first we have 3IT Helios, which is our solar park that we have here. So we have very large solar panels of different technologies that we test, and that we try to see what works well and what doesn't in our Quebec climate. And we also have some of these technologies also on the rooftops of some of the buildings at the main campus. We also have the 3IT Studio, which is a very large room where we have detectors pretty much everywhere on the walls, the ceilings, the floors, where we can test robots, drones, even we can even drive a car into this room and do a lot of prototype testing. We have the 3IT Mechano section, which is a mechanical shop. We have a lot of 3D printers, and we also build up a lot of our prototypes in this area. We finally have the 3IT Micro, which is where we do our PCB prototyping and device packaging. So we do have the ability at 3IT to make some PCBs. And finally, we're will be making these devices is the 3IT Nano. So 3IT Nano, okay. So the main research area for our lab is 3D electronics, biomems, energy, and ethics. So we have over 230 regular users. And to support, maintain, and manage this infrastructure, we have a team that's composed of technicians and research professionals with core expertise in pretty much anything from CMOS to surface chemistry, photonics, telecom, plasma etching. One person within our team is exclusively dedicated to providing services either to academic or industrial customers. So our team is not associated to a researcher, but the platform's management committee, which means that we don't privilege one researcher over the other one. It's really, our main goal is to maintain this infrastructure to its best, to maintain our processes, to make sure that our students are properly trained and use the facility in a safe manner. Everything that is developed in our labs, which is not covered by an NDA, is accessible in terms of a process to external users. We have a 450 square meters of class 100 clean room with a current extension of 200 square meters under construction right now. And we have 915 square meters of class 1000 clean room, including a class 2 biohazard. So this is where we do most of our characterization. We do have characterization in the clean room where we can actually stop the fabrication of a device, do in-situ testing, and then continue the fab. But most of the characterization is also done in that class 10,000, 100,000 clean room. That also will undergo construction extension, but not in the short term. So the building blocks, the processes that we use to build up a device, while someone was asking about gallium nitride, we process gallium nitride and make gallium nitride-based transistors in our fab. Actually, we process any material that we feel is non-contaminating. So if we feel a process or a material will contaminate, either we don't process or we limit its usage to a specific subset of the lab to limit contamination. We can process small samples up to wafers up to 200 millimeters in diameter. We have a laser writing machine where we can actually do direct photolithography on a sample or make a photomask. We add standard UV photolithography and E-beam lithography and beam writers as well. We have a very broad range of material deposition system. We have a CBE system where we grow 3,5s and gallium nitride. We have a lot of dry etching capabilities of a very large amount of material. Fib etching and deposition is also a capability that we have. We can do ion milling, ion implantation, and annealing. We have a very well-established CMP process and nano-damascene process. And we have a lot of characterization capabilities, both in the clean room and in the class 100,000 clean room, as well as a state-of-the-art cryogenic characterization system where we can go DC up to 20 gigahertz testing, very low temperature, very high magnetic fields. So this is typically the type of processes, and I call them building blocks, that we have in our facility. Now, what we can or cannot do with respect to electronic sensor platform, well, we are limited to 100 millimeter wafers or smaller, and that's limited by our ion implanter. We have a minimum spacing between each die of 200 microns. That is pretty much guided by the saw that we use to individualize these dies and some features that we add onto the die to prevent fractures from propagating on dies. We require also a 5 millimeter exclusion zone all around the edge of the wafer, and that is for our machines as well. Now, the next two constraints are more yield and cost related. Those are minimum feature size of 5 microns and alignment accuracy of 2 microns. Why is that? Well, it's typically because when we do something for an external service, it has to work the first time and every time. If not, we will have to repeat, and then the yield will go down and the cost will go up. So we limit ourselves for this platform to 5 micron in feature size and 2 microns of accuracy. We will add alignment features and test features. These will not be on any designs. This will be outside of the designer's design, so none of those will actually be seen by any user. We select the ion implantation and annealing condition based on what oxide we use, and as well as the doping level and profile that is requested by the designers, if specific requirements are requested. And also the annealing conditions are selected based on the metals that we use for the gate, drain, and source. So what is the base material for making these devices? Well, first we start off with a 100 silicon substrate N-type SB doped. They are 100 millimeter wafers, 420 microns thick with a resistivity between 0.006 to 0.02 ohm centimeter, and they are single side polished. The epi layer, which is on top, is boron doped, 1.6 micron thickness with a 3 ohm centimeter resistivity. Where we have flexibility is on the doping levels and depth that can be selected or changed per design. We can also adapt the material or the metal that we use on the drain source and bottom gate. Why is that? Well, that's maybe because an end user would like to do a surface treatment on their sample prior to adding their soft material. So maybe an aluminum contact would not be appropriate. Maybe gold is more appropriate. So the choice of metallization is a possibility. And also we have either the RTA or a furnace that could be used as an annealing method for metallization. This being said, we always select the annealing method, which is a known good recipe for good homing contacts, depending on if it's the backside, the end contact, or the P contact. All right, so how will we be making these devices? First, we start off with the epi wafer, we deposit oxide, and then we do the openings for the drain and source implantation. We implant the drain and source, but we also implant the backside of the substrate to get better homing contacts, because we feel that the base substrate is not, well, higher conductivity would be better. So we implant the backside to get a better homing contact. Once that's done, we anneal, and then we deposit the metal. First, the backside of the sample, which is a full backside gate. So that is an unpatterned contact. And then the top drain and source contacts are made and annealed. And then we passivate the top surface with nitride. And then we open up the contact pads and the channel on the top. So mind you, when we finish making these devices, this is an incomplete device in the sense that the active material on the top gate is not present. So once we've completed that, we need to singleize these dies. So typical dimensions is 1 centimeter by 1 centimeter, but we can always subdice into 5 millimeters by 5 millimeters. A perfect example of that is one of the designs that Priya told us about, which is a little bit smaller. If another die size is required, there's always a possibility of doing that. So that's when we have to talk with Priya to address any other specific requirements that is needed. Base IV electrical characterization is done. We do focus on the test features that we add to guarantee good homing contacts, and also that the base functionality of whatever is being made is okay. Mind you, we do not design these transistors, users do. What we do is make them based on good design, good fabrication practice, and minimize the risk. So when we do test a designer's die, we need to know what test conditions need to be tested, because we could very well break a device if we're not careful. We do have a lot of testing capabilities, so we could do more intensive electrical characterization if need be, and that if that's a requirement, we can always address that with CMC. We are very, very flexible in terms of what we can do, but mind you that if you submit a design you may actually be having 1/4 of a wafer of your design present. So if we change something for your design, we may need to consider the other designs which would be present on that wafer at the same time as yours. So from a fabrication perspective, we are super flexible. This being said, we always have to bear in mind the fact that this is a multi-user platform. So we always have to bear in mind the constraints of other designers. And if we change something, always addressable with PRIA, but we would have to consider also the other users that that would be using the same wafer as you.
The next presentation is brought to you by Mehrani. Mehrani, are you able to change the slide? Yes, please go ahead.
Okay, so thank you everyone for joining today. I want to talk about my project, which is a pH sensing JFET platform with printed graphene oxide gates. So currently I'm a member of Electronics Additive Manufacturing Lab, and our goal is to fabricate and deploy electronics in new ways for innovative applications. Some of our current projects are integration of 3D printing with printed electronics, structural composites with integrated electronics, and our latest project is integration of open-gate JFET platform with inkjet printing. So this project has many objectives. So the first objective is to design the open-gate JFET layout compatible with printed graphene oxide gate. Then we need to fabricate the graphene oxide gate on the open channels of JFET device and demonstrate the capability to pH sensing of fabricated devices. And the final objective of this project is to functionalize printed graphene gate for biosensing. So the ink that we used was made of graphene oxide nanopowder dispersed in water and ethylene glycol, and we made the ink ourselves. So before starting the design of the chip, we actually printed the graphene oxide ink on a silicon wafer to see the spreading behavior of the ink. So based on the printed lines, we chose the channel length for the design. And we also wanted to see the effect of different channel length on the measurements. So we added shorter and larger channels to the design. So here you can see the final design. It consists of different channel lengths from 10 micron to 200. And we wanted to have as many devices as possible on the same chip, so it would be easier for us to test them at the same time. And since we were using inkjet printing, it was very easy to fabricate the top gates all at the same time. So we also added some extra pads here in the design to facilitate the probing of printed top gates. So we can use these pads here to actually probe the top gates when we're measuring the IV characteristics. So after JFET fabrication, the design chips were diced into individual dies, and the outcome was 52 chips with a dimension of 5 to 5 millimeter. We printed each graphene oxide top gate 10 times to have a decent thickness, and we dried them after each printing at 70 degrees C for 15 minutes. And we needed a conductive top gate, so we actually reduced the printed graphene oxide lines with hydrogen hydrate to restore the conductivity. So the reduction process needed a high temperature, and the hydrogen hydrate is very aggressive chemical. So, but since we were using silicon platform, we didn't face any problem when we were using hydrogen hydrate. And we used 3 solutions to characterize the sensitivity of JFETs. What we did was we put a single droplet on each chip, and we measured IV characteristics for each devices. So here you can see 2 graphs. The left one is the IDVD characteristics of JFETs without any top gate as a function of pH, and on the right one is the IDVD characteristics of JFET with the printed reduced graphene oxide top gate. So in both cases, with increasing solution acidity, the drain saturation current decreases, and when there is no top gate, the pinch-off voltage decreases with changing the level of pH. The problem was that with the IDVD curves, we couldn't conclude anything. So we decided to calculate the output conductance and use it as a metric to show the change in the, show the sensitivity of devices for different pH level. The output conductance are extracted from IDVD curves with use of this formula that you can see here. And in the left graph, it is the output conductance as a function of pH for the JFET without the top gate. So as you can see here, with decreasing the pH level, the output conductance is first increasing and then decreasing for the devices without any top gate. But in JFET devices with reduced graphene oxide top gate, the device shows sensitivity to pH, and the output conductance decreases when the solution is more acidic. And the good thing is that the change in output conductance is monotonic, linear, and they all have the same trend. So when we have different gate voltages, they all follow the same trends. So we can actually use this graph here and calculate the output conductance for some unknown solution. And with interpolation, we can predict the pH of the solution that we're using. The other parameter that we actually used to show the sensitivity of JFET to different pH level was transconductance gain. Transconductance gains can be extracted from IDVG curve with this equation here. And we also wanted to see the effect of different channel lengths on pH detection. So as you can see here in the graph, when we have devices with reduced graphene oxide top gate, with increasing the channel length, the transconductance decreases, and for a specific channel length, higher acidity always leads to lower transconductance gain. And we can actually use this graph, and for a specific channel length, we can predict the pH of different solutions by using interpolation. So as a summary, this project demonstrates the integration of two complementary microfabrication techniques, and the results show that short channel devices perform better. And the JFET without the top gate shows some sensitivity to pH, but it is not enough to use it as a pH sensor. We are currently working on this project, and we definitely need more data point, but based on what we have at this moment, we can say that the reduced graphene oxide top gate shows sensitivity to pH, and the extracted data can be used to predict the pH of unknown solutions. And the other thing that we're working right now is simulating the whole project. So what we are doing is we're trying to simulate the reduced graphene oxide top gate with quantum ATK, and we're trying to add different concentration of hydrogen ions to simulate the top gate with different pH levels. Then we can extract some parameters like band gap or Fermi level, and use these parameters in CentOS to simulate the IV characteristics of a JFET device during the pH detection. And one of our other objective and our future work is to use the printed graphene oxide top gate and functionalize it with insulin-specific aptamer, so we can use it as an insulin detector.
Now, this next presentation is from Abbas.
Hello, everyone. My name is Abbas from York University, and under supervision of Professor Ibrahim Ghafarzadeh. We are using open gate JFET and actually investigating its capability for being integrated with microfluidic for overall neutrophil detection application. Okay, our application is we are trying to use open gate JFET for as a platform, sensing platform for high throughput oral neutrophil detection. Actually, this is a actually sensing platform for high throughput screening of infectious diseases. As you can see, we are integrating the OpenGate JFET with a microfluidic chip for delivering the sample from patient to onto the sensing area of the JFET. And then after sedimentation of the cells and the surface charge will be changed, and afterwards we will be able to quantify the concentration of neutrophil cells by JFET. Why we used OpenGate JFET? Actually, OpenGate JFET offers large sensing area, as you can see in the picture, and also it offers very good, easier integration with microfluidic because of its enough space on top of the sensor for integration of the microfluidic. And also a very important feature of the OpenGate JFET is that there is no need for reference electrode, and that helps to have better integration with microfluidic for point of care devices. Next slide, please. Okay. In our design, actually, we considered the integration of microfluidic and from the first. And for example, we considered the distance from pads and also the channel thickness to have a microfluidic channel on top of the sensor. And also in our design, we tried to do multiplexing. For multiplexing, for that purpose, we designed 7 drains and 1 common source, as you can see in the picture. And so that helped us to have better analysis of cell attachment on different parts of the sensing area. And also we use simulation and before fabrication to get some dimensions and sizes to estimate gain and sensitivity for having a better design. Next slide, please. We use COMSOL simulation based on design rules that is offered by CMC. In COMSOL, actually, we could get IDS, IDS, and VGS curves for both reverse and forward bias. And actually, COMSOL simulation helped us to estimate the gain, transconductance, threshold voltage, and sensitivity for estimating the sensor response before fabrication. And COMSOL also helped us to have parametric design of OpenGate JFET based on design rule and environmental, and estimate environmental condition effects on the sensor. As you can see, the IDS-VDS curve is very similar to experiments that actually very similar to our experiments. Next slide. Also, we use COMSOL simulation as a platform for estimating the fabrication origin errors and estimate those effects on the sensor response. As you can see, we have different parameters in OpenGate JFET, for example, P-channel thickness, P-channel doping, and P-channel length. So we can estimate the errors that comes from fabrication and estimate those effects on the sensor. We actually, based on our design, we understand that P-channel thickness is very important to be considered, as its effects is higher, as you can see, compared to other parameters. Next slide, please. Also, we are using multi-physics power of COMSOL to improve our design. Based on our application, we needed to have fluid flow, electrostatic and diode species, and semiconductor to design our sensor. As you can see in our design flow, first we designed the fluidic channel and fluidic parts, and then estimate the concentration and analyze the distribution. And then from that, we estimate the surface charge and pH effects. And we use those information as input for semiconductor design of the sensor. And also we can use this platform for multi-scale design of the biosensor, considering different antigen antibodies and for other applications. In order to do our test, we needed to have continuous microfluidic and continuous flow for operation of the biosensor, our biosensor. We needed to load cells on top of the sensor in a continuous manner. So we designed a fixture for our integrated microfluidics. As you can see, our fixture consists of a microfluidic channel on JFET. The microfluidic channel has been fabricated by replica molding, based on replica molding for continuous flow analysis. And the fact our fixture can be connected to semiconductor analyzer, so there is no need for probe station. And also the structure for holding the sensor can be 3D printed, and for creating that structure. And next slide. The very simple fluidic test that we did, it was very important to test the sensor in continuous flow. As you can see, the dry JFET and the response of the dry JFET, and when we added the DI water, and afterwards, immediately we applied NaCl solution to the sensor, and we could see very perfect response time. And as you can see, we can see that sensor is very sensitive to change in concentration of the solution and ion solution in the environment. Very important parts of biosensing development is to understand the standard response of sensor to pH to the pH and ion concentration. Actually, we used open gate JFET and operated that without using any bulky reference electrode on top. Actually, because we have the advantage of back gates in the structure, and we only use back gate to operate the sensor. And as you can see, we could get a very good sensitivity of the sensor, very linear, that is compatible with the other standard ISFETs available in the market. Actually, this is under the NERS limit, which is the 59 millivolt per pH, and JFET actually shows very perfect sensitivity toward the pH. This is a standard curve that can be compared to other available ISFET in the market. Next slide, please. Another mode of JFET operation is constant voltage. Actually, the back gates of the JFET is a huge advantage compared to other available FET sensors, as we can use the back gate to change the sensor operation point, and also having different sensitivity with actually change of the back gates voltage. And as you can see, if we consider the pH as our input, we have completely linear response that is amazing, I think, compared to other sensors. And also, as you can see, the slope of curves is different based on change of the back gate. So we can use back gate to have different operation points for based on our need in different applications. Next slide. For our application that is detection of neutrophil for COVID-19, actually studies showed that there is a correlation between the number of neutrophil and COVID-19 status. in patients. So we actually we have isolated cells, neutrophil cells from saliva, and in our next step we are gonna capture the cells on top of the sensor with microfluidics, and also after cell adhesion, the cell adhere on the surface, the local pH will be changed. So we will be able to measure the sensor response based on different concentration of the cells in the microfluidic channel. And also we are using COMSOL simulations, COMSOL package for estimating the trap cells on top of the sensor, and then use those data for our design. Next slide. Thank you so much. Thanks for your attention.
Thank you for your presentation. Just a quick note here that both these projects were supported through MyTax internships, which were with CMC as the partner organization. Now, I'll just end with a few slides here on how to participate in the upcoming design run. The schedule of this run is shown on the left side. So anyone who's interested in participating in the upcoming run, we would like to start engaging with you immediately to help familiarize with your design and packaging considerations. The application deadline is May 26th. And for the first time, what we are also planning to have is a training that is specific to ESP PDK, along with an introductory LEDit training, which would help you in your design process. As you saw from the two user presentations, there are so many considerations that you need to take before fabrication, such that it meets all your criterion, all the way to testing and packaging, which comes way later in the process. So this training will be provided by none other than Marianne, who is the founder and CEO of SoftMems. Together, we want to ensure that you design right your first time. Now, once the design is completed, it gets taped out to the fab, and the typical turnaround time for these chips is 3 to 4 months. And the baseline process is as shown on the right side. I think Marie-José covered most of these points here. So the only thing that I want to highlight is the heavy discounting we have that is going on at this point to fab your chip with us. I strongly encourage you all to make use of this at this point.